next speaker is young Kalin, right? Oh, sorry. That's the one.
You could reduce the light of the turbines.
Those?
Yes, a little bit.
Good morning. My name is Jan Kalin, and I come from the Slovenian National Building and Civil Engineering Institute. And I'll give a short presentation about the comparison that we did two numerical codes from hydraulic and transport technology. Now, to put things into context, Slovenia has one nuclear power plant, and our team was performing performance assessment, safety analysis studies for the future low and intermediate level waste repository. Now, the general approach for this is that you divide the problem into three parts. So the near field, that is the repository itself and the near surroundings, the far field or the geosphere, and the biosphere. In our studies, Hydrus was used for the near field by our colleagues from Geological Survey, and the team began cooperation with COA from France in 2007. And there we learned about ElNesr, which is a platform co-developed by COA, Andra, and ElNesr. It's written in Python and ties together various numerical codes. For instance, Kalin, which is the solver that we use, flow, Krivic, and so on. And the task was to investigate whether we would use ElNesr first of all, for verification of Hydrus results, so that we would have two completely different codes doing the same problem to see what we got out, and if we could use ElNesr for further work. Now, the structure the problem that we compared was a silo-type repository for low and intermediate level waste. This is a vertical structure buried in soil. Its inner height is 33 meters. The diameter, the radius is 12.8 meters. The silo walls are 0.9 meters thick. The waste is placed into concrete blocks, and the blocks are then, and the silo is filled in layers of 70 concrete blocks. And the voids between the blocks and the silo are filled with drainage gravel. So as I said, this whole thing is buried in silty soil under water table, so we're in saturated conditions. In the area, there was previously measured the general horizontal hydraulic gradient, and we chose it to be so that the water flows from left to right in the model. We can neglect the top and the bottom of the silo, and then by that we're being slightly conservative. And of course, by that we can make just a horizontal 2D model without going into the 3 dimensions to model the whole silo. As we're in the saturated conditions, we only need hydraulic conductivity. So either 10 to the minus 10 for concrete, meters per second for concrete, 10 to the minus 7 for silt, and 10 to the minus 3 for gravel. And we also simulated barrier degradation. So in effect, what we did was we increased the conductivity of concrete to that of silt. So after 10,000 years, we assigned conductivity of silt to silo walls. And after 100,000 years, the blocks themselves that contain waste also became silt. And this is an example of the velocity field in the undergraded state. So here you can see this is the silo wall. So almost all of the water goes around it. Some of it goes through the silo wall, but almost none of it goes actually through the repository, because there's a preferential pathway of high conductivity. So 7 orders of magnitude higher conductivity in the drainage gravel. But when we compare the results, we compared the sea velocity in this region here, so at the center of the silo, but when we compared results, it turned out to be very different from what Hydrus got. And when we talked to our colleagues that performed the actual calculations with Hydrus, it turned out that they had difficulties with different conductivities, because they had numerical instabilities on the boundary between concrete and the drainage gravel, because there's a part where there's concrete, so very low permeability, then you have high permeability gravel, and then again very low permeability concrete in close vicinity. We're talking about 5–10 centimeters. So what they did was, instead of gravel, they used conductivity of silt. And when we redid calculations with that, you can see that the numbers match quite well. In undegraded, in completely degraded state, we got the same result. Here there's a factor of 2 and a factor of 5. Up there, if you see previously, the differences were 3 orders of magnitude. So now, and also the transport calculations, of course, are performed after you get the velocity field. So you impose the rescue velocity field, and you calculate how that water transports radiant nuclides. So we model advection, diffusion, dispersion, absorption, and decay. We assume that the waste is uniformly spread in the containers, and that it is completely solved at the start of simulation. And in the previous study, we shown that concentrations everywhere are far below solubility limits, so that's a reasonable assumption to make. We measured total radionuclide flux through the downstream boundary. So as the water flows and the exits, we measured the flux on the downstream boundary. And we compared the height and the position of the flux peak that comes out. The calculations in Hydrus were performed only up to a million years. That was a requirement of the regulator, and it also took relatively long to calculate, so the team that performed the Hydrus calculation didn't go on further. But that means that for some of the peaks were not reached. So for the uranium and americium chain, the peaks were not reached. In Alliance, we decided to go up to 10 billion years, of course, by the time the probably destroyed. But anyway, we got all the peaks, so everything had decayed by. Now, one thing, in the Alliance solver uses a fully implicit scheme for calculation. That means that it is unconditionally stable. That means that when you're doing time steps during simulation, you can use relatively large time steps, and it does not explode. But you have lower accuracy at larger time steps. So so you need to find the correct time step for the simulation to get the accuracy that you desire. What we did was use the strongest sort I beam to check accuracy. So we turned off the decay, and we integrated the flux coming out of the right boundary. And of course, the integral of the flux must be equal to the starting amount that you put into the repository. And we tried different time steps, and at the end of the chosen time step, there was a difference of 0.5% between what we put in and what came out, and which is more than enough for comparison. And in fact, for all radionuclides, the mass balance was better than 1%. And these are the results. So you can see that these are the chains that I was talking about. So the uranium-238 and americium chain. And these are the radionuclides that are less salt than come out before. So here, this one here is iodine 129. This one is this is magnesium 99. This one here is the tritium, because of course tritium is not sorbed, so it's not retarded. That means that it comes out immediately with the water flow. So as I said, the uranium and americium chains were not compared because the peak in Alliance is at about 1.2 times 10 to the 7 years. In Hydrus, we only calculated up to 10 to the 6 years, so we couldn't compare these. The fluxes of cesium, strontium, and nickel, nickel 63 were less than 10 to 31 becquerel per year, and in the analysis, the previous analysis, they were not even considered. The difference in fluxes of carbon is 7 orders of magnitude, which is, of course, quite a bit. Turns out that there's a difference of 136 half-lives between peak positions in Alliance and Hydrus. In Alliance, the carbon comes out much quicker. But they're low anyway. They say 10 to the minus 11 becquerel per year, which is completely negligible when you're talking in the context of safety analysis. The fluxes of chlorine 36 and niobium differ by an order of magnitude, and for that we couldn't find an explanation because the peaks were at the same place, all the parameters were the same, but there was a difference of 10 to 20, by a factor of 10 to 20, so we have no explanation for that. But the fluxes of iodine 129, technetium 99, and nickel 59 match within a factor of 2. And that is very good, because it's exactly the iodine 129 and nickel 59 that contributes by far most to the total dose in our models. So we can be sure that we got the right results. The flux of tritium again differed by 3 orders of magnitude. As we said, tritium is not salt, so it's not retarded. It has a short half-life of 12 years. The peak comes out at, the peak is about 220 years. That means that if you miss by 10%, you already have two half-lives difference. We thought that the C field details could have a large influence on when exactly the tritium comes out. So what we did was we tried to, we then modeled, we applied different meshes to the repository. So we repeated all calculations with 2 finer meshes. Okay? You can see the first on the left is the original mesh, and a little bit finer mesh, and the finest mesh. And this is the detail at the bottom. So where the silo wall comes down here at this lower right edge. Different time steps did not have much effect. However, the effect of mesh density was very, very large. And the finer the mesh is, the later the peak appears in the output. So apparently a coarser mesh appears to overestimate their sea velocities. And as you can see, this is really, really, really large difference. As you see, there is a 4 orders of magnitude between the coarsest, between the results from the coarsest mesh to the finest mesh. We also did the same thing for iodine 1 to 9, but in this case the difference is not that much bigger because most of the iodine, I mean the peak comes out, as we said, at about 1 point. So the peak of iodine is after everything has been degraded, and that means that once everything is degraded, the whole model is that, or the whole field has actually uniform permeability. That means that the mesh itself has no effect because the Darcy velocity field is homogeneous and is homogeneous at that stage. So in conclusion, we'd say that for the 2 most critical radionuclides, the results match very well. We also found that mesh details, as we've shown, can have a very strong influence, especially for short-lived radionuclides. And in any real calculations, mesh details should also be included in sensitivity analysis. And of course, it would be interesting to run transport calculations with 3 conductivities, not with 2, but we didn't have time or there the mesh details should be even more influential because, as I said, we reduce by two conductivities. You have 3 orders of magnitude of difference between conductivities, between concrete and the drainage gravel or sill. There you have 7 orders of magnitude, so these effects should be even bigger. And at least for saturated transport, the Alliance has a major advantage in terms of speed. So it's said the calculations for one radionuclide for 10 to 10 years take about 5 minutes on with Alliance. So and with that, I would like to thank the organizers for the invitation. I'd like to thank you all for listening. And of course, if there are any questions, feel free to ask.
Because of the standard here or the law, assume that we need to run for.
No, it's like this. So our regulator requires calculations up to 1 million years. But in, as I said, in Alliance, the program is so quick that it doesn't matter if you run it for 1 million years or if you run it to 10 billion years, because the difference in real time, in computer time, is maybe 50% or something like that. So we just said, okay, we'll make sure that everything comes out of the repository. That was the only reason that we went there, because we could. Yes, please.
Yes, the difference is 1 million years, 10.7 to 10.6. Why don't you make the 10 to the power 6 and input to another simulation to complete the result, the simulation?
I don't understand. What do you mean?
You said that Hydrus can simulate up to 1 million years.
No, we used Hydrus and we stopped simulations at 1 million years.
Oh, it can simulate more?
It can simulate longer, yes, but the thing is that these calculations were done in about 2006 or something like that. And the speed of computers wasn't that high.
Yes, I got it.
And the calculations for all the 15 radionuclides that we had in our study took over a week for up to 1 million years.
Yes.
And we said, okay, that's enough. We don't need any more results. That is it. Yes, please.
But the mesh sensitivity.
Yes.
First, did you see a difference between the mesh density in Hydrus and compared to aliens? Did you see any difference on the sensitivity?
So yes, I forgot to say that. So the Hydrus results, we could not do anything with the Hydrus results more than just take them, because as I said, it was done some time ago. So we got the mesh that was generated in Hydrus, I mean that we used for Hydrus, and we couldn't make a different mesh in Hydrus. So all this was done only in Alliance. We couldn't perform those sensitivity studies in Hydrus because we didn't have time and funds for that. So only in Alliance did we do this sensitivity studies.
And how do you deal with the sensitivity? Let's say the real mesh sensitivity.
Mm-hmm.
How do you deal with that? What do you do exactly?
Well,
you change the.
The thing is that the Alliance is a very interesting package. You can it's written in Python, and you control with Python the low-level numerical code, including mesh generation. That means that you can actually just say have a parameter, number of elements in the mesh, and vary that programmatically. So in this case, what we did was we just generated 3 meshes. But that was as simple as saying, I don't want 2,000, I want 4,000 elements. But this parameter could also be used as a parameter in a sensitivity study.
Thank you.
So the next speaker is Betty May.